Hi, my name's Tom Hull. I'm the Vice President and Chief Information Officer at Pace University. Today I'm going to demonstrate whiteboard paint called IDEAPAINT. This is paint that you can put on any flat surface and it becomes a whiteboard. At the Advanced Technology Lab here at Pace University, we've used it on this wall. As you can tell, it's a flat surface. Here's the existing wall, and here's the area of the wall that we painted with whiteboard paint. Now today, let's give it a workout. I'm going to prove Albert Einstein's E equals mc squared equation on this whiteboard. So let's get started. Let's define a set of coordinates out in space-time called z, x, y. And we'll give those series of coordinates a system name A. Out here in space, let's define a body of mass. We'll call that body of mass P. Let's let m equal the mass of P. Now, we let P move in the positive z direction, like so. We know that the momentum of P equals its mass times velocity, momentum of P. Now let's also introduce two light energy complexes into this area of space. S prime. These are equivalent light energy complexes, and we'll move those in the positive and negative x direction towards mass P. As P is moving in the positive z direction, an angle is formed here. This angle we'll call alpha. Now alpha, by the definition of the aberration of light, equals the speed of light over velocity. Let's let E equal the total energy of our light energy complexes S plus S prime. Because those two are equivalent, we know that E over 2 equals the energy of S or S prime. Now, by Maxwell's theory, we know the momentum of one of these light energy complexes equals E over 2c by Maxwell's theory. Now, when V is small as compared to c, then the momentum of those energy complexes is the same, except for the quantity in the second order of magnitude, in which v squared over c squared is small as compared to 1. In which case we get the momentum of one of those light energy complexes is E over 2c sine alpha. Now, in the higher order of magnitude, the z component of this momentum of one of those light energy complexes, E over 2c alpha, again in the higher order of magnitude, equals E over 2v over c squared. That's the momentum of each one of those light energy complexes. Now together, we know that the total momentum of those light energy complexes is E times v over c squared. The total momentum then for this system of mass and energy we know is mv, which is the momentum of P, plus the momentum of those light energy complexes, E times v over c squared. Now, as P absorbs this light energy as it moves through space, it gets a new mass. That new mass we'll call m prime. Then we know the new momentum of that mass is m prime times its velocity, which equals the total momentum of what it absorbed, equals mv plus ev over c squared. In which case we can simplify the equation by removing the v components. We get m prime equals m plus e over c squared, which gives us, by the law of the conservation of momentum and the conservation of mass, we get m prime minus m equals E over c squared. We've shown a relationship between mass and energy. We know that energy always leaves an additive constant free. Therefore, E equals mc squared. Now, we take this Albert Einstein's well-known equation and we apply it to Pace University. So let's let our mass body P in system A, PA, equal the mass of that body, which is m. Therefore, we get E equals PAC squared. Now let's let E equal the speed of light. E equals c. Therefore, we get big E equals PACE. So there's a lot of energy at Pace University. So today, as you can see, this whiteboard paint works very well. It stands up to a big test of working it out with Albert Einstein's well-known equation. And thanks for watching. We're very pleased with this whiteboard paint called IDEAPAINT here at Pace University. I'm Tom Hull, Vice President and Chief Information Officer, and we look forward to using more of the IDEAPAINT. Thank you.